as I mentioned, the free volume is a useful concept in specific fields of material science, and it can be certainly described and defined in other in other materials. But there are other ways how we can describe the structure of the materials that can be more useful in certain aspects. So one extremely useful concept that we will introduce and come back over and over again throughout the semester is the pair distribution function. By the way, so these are called generic descriptors. So the generic descriptors, the free volume and the pair distribution function, simply means that they can be applied to any type of a material. So I can define the free volume in a crystalline and non-crystalline material. I can use the pair distribution function in any, right? So they're very generic. So when we start to talk about some of the descriptors for crystalline materials, they cannot be applied for non-crystalline, right? So these are generic. They can be used for any type of material. So let's talk about the pair distribution function. It's a very, very useful function that can be measured from neutron diffraction, from X-ray diffraction, etc. And it's one of the major measures of how you can describe the structure of materials in general. So what I have here represented are blue atoms, and we will think about atoms now as hard spheres. So they are they have certain borders, and the white dots represent the center of that atom. Okay. So, and for this particular case, we don't know necessarily if there is any ordering within this material. So it's just a general material. Atoms are somehow distributed in space, and we don't know anything about the ordering. So then I will define a specific atom, and we will see that the choice of the atom does not change the end result, right? So the choice of the atom that I'm selecting in this particular case is irrelevant. I can choose any other if you assume that this material is infinite, right? So then I will draw a circle, and you can imagine that now this drawing in 3 dimensions. Now I'm just drawing this in 2 dimensions, and we are imagining that this is a 2-dimensional crystal. And I'm defining a shell around it that has a certain thickness, which is dr. We will see that this dr is arbitrary, but the definition of the function will go when this is a limit, when this thickness of this shell is going to 0. Okay? So basically, I'm taking one atom, I'm making a circle around it, or a sphere around it, and that has a radius r, and I'm making then a shell of a certain thickness dr. And then I'm counting how many of the atoms do I have in that shell. In this particular case, 2 of the centers of the atoms are within this shell. And let me again remind you that we are counting an atom being in a shell when its center is in the shell, right? So for example, I won't be counting this atom because I'm not counting the entire atom. I'm counting this atom as 1 when I hit the center of the atom, right? So then the pair distribution function will be defined as follows. So we will call it gr. So at a certain distance, r, it will be the number, which I will call dn. It is the number of the atoms at a certain distance in a shell that has the thickness of dr, divided by the volume of that shell. And again, this is at the radius r, and the shell itself has the thickness of dr. So I'm simply counting the number of the atoms in this shell, and then I'm normalizing this to the average density of the material. So this average density is simply the number of the atoms per volume in that particular material. You seem to be puzzled. Yes?
What are all the symbols?
So this is dn, this is r, this is v. Okay. Okay, let me try to write this. Let me try to write this a little bit neater, okay? Okay, so d, n. At a certain distance r of the thickness dr, normalized to the volume. Better? Sorry? So this is the number, dn, the number of the atoms at a certain distance r for the thickness of the shell dr, normalized to the volume of that shell, and the shell itself has the radius r and the thickness dr. Okay? And so all of these are defined here. Okay. So the question is, so we now define this function, right? Is the number of the atoms or the density of the atoms within that shell normalized to the overall density of the atoms within that material? So how do we understand this? So I will certainly give you a couple of examples to show you how this function looks like for crystalline, non-crystalline materials, etc. But what is its meaning? So you can think about this fundamentally as the probability of finding an atom at a certain distance from an atom within the material that is normalized to the overall density. Okay, so I will write this down. It is probability of finding an atom at a distance r, so this is r, from a typical atom. Okay. So again, throughout the examples, hopefully this will become clearer, but it basically tells you what is the local density around a typical atom, right? So if you think about the material where you have small clusters, so then the probability of finding an atom around a certain atom will be relatively high. And if you imagine that these clusters are further apart, then this probability suddenly drops beyond that cluster. Okay? And let's try to simply to see a couple of examples and try to understand what that means. But before we do that, let's try to understand this in more details. So if you simply look at this definition, which is now typed neatly, we can think about it. What are the units of this function? Yes? It doesn't have units, that's right. So we are simply counting the number. So this component, it's counting the number per volume, and we are normalizing to this to the overall density or the number of particles per volume, right? So it's unitless. Another question that I can ask you is, does it depend on the thickness of that shell? So the way how I define this, right? So I just told you that this is the definition. I'm drawing this circle and I'm making a shell that has a certain thickness, dr. And I can ask you a question. If I have the same material and if I define the thickness of that shell in a different way, would the function look exactly the same or would it change? Let's take two extreme cases. So if this dr is really large, it's infinite. And if this dr is very small, if it's infinite, what would be my pair distribution function? So if you simply imagine that this is infinitely thick, then you're basically, this pair distribution function is 1, right? So you're simply counting all of the atoms within the material and all of the volume of the material, and you're normalizing this to the density, right? So it's simply 1, right? But if the thickness of this is relatively small, then the pair distribution function is the function of where you're defining this sphere. Okay? And again, let me show you a couple of examples, and hopefully the things will become a little bit even clearer. So just to answer this question, yes, it does depend on how we define the thickness of this shell. And we are typically thinking about this pair distribution function in the limit when the dr and the volume are going to 0, in the limit of the 0. And I would encourage you to check the example from Allen and Thomas. So this is an example from Allen and Thomas' book. It's example 3 from chapter 2. And it simply gives you the pair distribution function for an arbitrary material that is described here. So all of these individual circles represent individual atoms within the material. And then the pair distribution function is calculated simply by counting the number of the atoms when the thickness of this sphere is changed and it's doubled or halved. So you can see that the result, which is shown in the solid and in the dashed curves, is slightly different. So it's becoming finer and finer when this dr goes to 0, right? So if this shell is thinner and thinner, you're seeing more and more features, and they're telling you more and more information about the structure of the materials. Okay, so let's try to see a couple of examples. So for a crystalline material, So if I plot the probability that I will find an atom, so this is my pair distribution function as a function of the distance r, it will be 0 until I hit a certain distance. And that particular distance is simply twice the radius of an atom. So if I think about two atoms as hard spheres, one atom is at this position, and the very first position of another atom can be when they are touching each other, where this radius is labeled as r naught. Right? So the smallest distance in which I can put two atoms next to each other is when they are touching each other. So in crystalline materials and in all of the materials that we will check or investigate, so the pair distribution function has the value of 0 until you reach the value of 2 r naught, where r naught is the radius of an atom in this hard sphere model. So in this particular case, we are looking, for example, into individual atoms. So I'm selecting this atom here, and I'm counting how many atoms are around this particular selected atom. And when I hit this 2 r naught, I suddenly have 6 of them. Right? So the pair distribution function will be a very sharp increase. And very often in crystals, we are counting the number of the atoms at a distance r. And this then would have a value of 6. Then the pair distribution function is, again, 0 until I reach the second shell of the atoms. And if you do the geometry, if it will happen to have, in this particular hexagonal crystal, it will again have 6 atoms. If I count them, there are 6 of them. And there will be the distance at 4 r naught cosine 30 degrees. And again, if you do just the geometry, you would learn that this is really correct. Then the next shell is at the distance of 4 r naught. And again, there will be 6 atoms in this shell. So what this particular example tells you is that the pair distribution function is simply a set of discrete delta points at certain distances from an atom. So other thing that we learned is that for all of the materials, regardless of they are crystalline or non-crystalline, the pair distribution function will have value of 0 until we reach this critical 2 r naught value, right? So if you see a pair distribution function and it looks like a set of delta points or very sharp points, it means that this material is crystalline. So if I have X-ray experiment, if I measure the pair distribution function, and if this is my result, I know that the material is crystalline. Okay? So let's see how this pair distribution function will look like for non-crystalline material in general. So this would be non-crystalline material. And again, I'm plotting the pair distribution function as a function of the distance from an atom. And how this pair distribution function will look like is, again, the value will be 0 until I reach 2 r naught. Again, r naught is the radius of a hard sphere atom in this model. And then the pair distribution function will increase like this, and it will be a structure that looks like this. And then eventually it reaches the value of 1 at a certain distance. And again, we will go into details, and I will tell you about what is the meaning of this. But we will go into details of understanding what these peaks are and what they mean. But if you, again, have an X-ray diffraction, and the pair distribution function that you calculate and measure looks somehow like this, then your material is amorphous or semi-crystalline or non-crystalline. What that, again, means is that there is a certain probability that we will find an atom at a certain distance, and there is some ordering, so there is some probability that we will find an atom at a certain distance, but then after a certain distance, that probability is just random. So there is no correlation between the atoms. So let's look at this particular graph in more details and try to define things here. So first thing is, I can ask you a question, is what is this value here? So we know that the closest distance that the two atoms can have is 2 r naught. But the very first peak in this particular graph tells you what is the average distance to the first shell of the nearest neighbors. In other words, if you have an amorphous material and if you have some ordering within the material that is short range, this distance here, the very first peak, will tell you what is the average distance of the first neighbors. So if I'm a silicon atom in silica glass, this will simply tell me is how far the nearest oxygen atoms are. Okay? The closest that they can be is that when they're touching, and very often this first peak is relatively close to this value of 2R0, but on average, the distance between these two atoms will be at this very first peak. And again, notice that I'm telling you about average, right? On average, so this particular function tells you what is the average distance between the atoms. It doesn't tell you what, if I have a particular atom within the material, what its first neighbor will be. It tells you on average in that material, this will be the first distance. So then I can ask you a question. So this would be the second peak, would be the second shell of the nearest neighbors. And I can ask you a question of why there is a valley here. It tells me, so what this valley tells me is that a certain distance, after I pass the first neighbors, suddenly the probability of finding another atom goes down suddenly. Yes? So the answer was that outside of the first shell, there are small gaps. That is what exactly this graph is telling you. The question is why there is a gap. So in other words, so if I have the first neighbor, right? So this is my first neighbor. And there is certain probability that I will find an atom at a certain distance, right? And then suddenly, soon after this distance here, the probability of finding another atom drops. Yes?
Because the first neighbors take up space?
Exactly. The answer is because this first neighbor takes up some space, right? So I can't physically put another atom here, right? So they can't sit in the same space. So there has to be a certain distance, at least in this direction, where they can sit, right? So there is a decreased probability that you will find another atom because this space is already occupied by the first shell, right? So this is the reason why you have maxima and minima in this function. Another important thing to remember here is this distance, xi. So this is simply the distance where this pair distribution function reaches the value of 1. And this is so-called correlation distance. So this is the distance in the material after which there is no ordering whatsoever. You lose any information about the correlation between the atoms, right? So again, if you imagine our silica material, I know exactly where my oxygen atoms will be in the material. Maybe I have a power to predict where the next silicon atom is. But beyond that point, I don't have a clue where the other silicon atom will be, right? And depending on how well I can define this or how this is well defined in terms of the ordering within the material, this correlation distance xi will change, right? So if I have a material and the ordering on the short range is more enhanced, this correlation length will be longer. It simply tells you what is the distance at which I can, at certain probability, predict where the atoms will be within the material. Okay? So again, in the recitation, you will go through a couple of other examples, and hopefully this will be solidified, the knowledge. But the other question is, if you look at the gas, right? So we are looking at different structures of the material. So by the way, this pair distribution function for liquids and amorphous materials looks relatively similar because their underlying structure in principle is similar, right? So what happens for a gas? So how would the pair distribution function look like for gas? In the gas, the atoms do not have any correlation, so they can be any place in the available volume, right? And the closest distance at which they can be is still 2R0, right? So for any material, the function will be 0 until we reach 2R0, right? So how this function will look like, it will simply go to value of 1, and it will stay there. Right? So at any distance, so if I have so actually I do have atoms here, right? So if I have an atom, this atom doesn't really care where the first atom was, so it has the equal probability of being here or where it is shown here, right? So it tells you that the probability for finding an atom in a gas from a certain atom is equal So it can be 2R0, that's the smallest, but then we really don't know where it is. So that again tells you there is no information about, there is no short range order, right? Okay, so in the interest of time, I will leave this discussion about labeling all of the things. It's just a sanity check. It is just repetition of what I just mentioned. You might want to do this at the recitation, but it's just basically telling you to label everything just to, reconsider whatever we just talked about just once more, and try to think about how would this function change if you, for example, heat or cool the material, right? So if this was a glass material, amorphous material, and we know it's an amorphous material because it has these wiggles. It's not defined, it's not crystalline, it's not gas, so it's kind of an amorphous material that has relatively long range order. So there are at least 1, 2, 3, 4 nearest neighbors. So this is relatively long ordering in a non-crystalline material. And then what happens with this pair distribution function if I heat that material? So if I take XRD diffraction, or if I do anything to calculate and measure the pair distribution function, and if I heat the material, how would this change, right? Or if you process the material in different ways, how would it look like? Okay, so we introduced these generic functions that tell us about how we describe the structure of non-crystalline materials. And what we will do next time, and I would just like to give you a very first hint. So next time we will specifically talk about how do we understand how, for example, typical glasses or polymers, how their underlying structure looks like. So we can use the pair distribution function then to describe this in more details. But for example, if you have window glass, and if you think about this, what is our current knowledge how these materials look like, at the atomistic scale, and what kind of ordering they can have. Another class of very popular amorphous materials are polymers. And again, we will specifically talk about polymers. But I just wanted to tell you that again, as we mentioned last time, is that in principle, any material can form a non-crystalline form depending on the processing, right? So even the metals that can that are typically crystalline materials, they can exist in amorphous form. And I won't go into details. We can talk about the processing methods next time, how you actually prepare these materials. But just to give you the keywords of the things that we learned today, and just to show you a very short video that introduces the processing of the glasses at the end. So the keywords, so what we learned today is that we again solidify the knowledge of what the short versus long range order is. So if someone wakes you up in the night after taking this class and asks you what the short and long range order is, you should know it. Okay? We introduced the concept of descriptors. And the two descriptors that we talked about are free volume and the pair distribution function. Okay, so these are the things and keywords that hopefully you picked up throughout the course. And again, hopefully through some of the examples and problem sets, you will learn more about the details. But just to give you a short introduction of what we will learn about next time, I would like to show you a video. So most of you are probably familiar with this movie. Do you know this movie? Very cheesy romantic comedy, Sweet Home Alabama. And I wanted to show you one clip from the movie that tells you something about the processing of non-crystalline materials. So it's the very beginning of the movie. So I don't know if you will hear the sound, but there are two kids on a beach. And it's very rainy and so I apologize, it's kind of dark, but they're running on the beach. So there is lightning, so there is beach, right? So there is obviously sand. Okay, so what happened there? What did they find? So they found glass. So for those of you who know the movie, the guy happens to be an artist who makes glassy things at the end. But the reason why I introduced this video is just to tell you that, again, you start from a crystalline material, start from sand, right? And then you provide a huge input of energy, you heat this very quickly. And because it cools very quickly, it forms glass. And these are the types of processing methods that do exist in nature. But again, the question is, why do you end up with the glass and how quickly you have to cool that, right? So in the case of sand and glass, the natural cooling is sufficient to produce glass. But we will see that, for example, in metals, this cooling has to be much, much quicker, okay? So these are the things that we will talk about when you return after your labs. So let's have a break and enjoy your labs.